All right, Science 10, we're back and we're going to keep looking at this concept of reduction and oxidation reactions. And we're going to do a little bit more real world application, but we're going to use that to help us learn how we determine um, what kind of reactions are going to be happening here. So give me a second to just quickly bring up the slides here. And we're going to start talking about everybody's favorite shiny metal, gold. Now, gold has a very attractive appearance. It's shiny, it's pretty. We like making jewelry out of it. However, its physical and chemical properties are what makes it a very precious metal. Now, gold is the most malleable and ductile metal known. Now, remember, malleable means we can shape it, ductile means we can stretch it into a wire. So we can hammer it and stretch it into whatever shapes we really want. It's also a really stable metal. It does not react very easily with other elements. My wedding ring is made of gold. It doesn't tarnish. It doesn't react with most strong acids. And so I don't have to worry about, polishing it up every now and then like we have to do with silver. So from a chemical point of view, it is almost indestructible. And so, and the reason why is because the gold atoms hang on to their electrons a little bit more tightly. So corrosion and tarnish, not very likely going to happen. Therefore, things like oxidation going to be very hard for gold to undergo. Now, it is possible, but uh, not not very easily compared to other metals. So if gold is the least reactive metal, that probably means there are some metals that are more reactive. So which one is the most one? Is there a way that we can compare the reactivity of one metal relative to another? The answer is yes. So when we talk about gold and silver, they are considered to be precious metals and that they do not participate easily in reactions. At the atomic level, the chemical reactions are going to occur when electrons are being exchanged. So they don't really form a lot of ions the way that we normally look at it. And so they don't usually lose their electrons very easily. However, their ions have a high tendency to react. So the silver ion is very likely to gain that electron, to be reduced, undergo reduction. See how I'm using different ways of saying the same thing here. Gaining electrons, being reduced, undergoing reduction. All of those three phrases mean the same thing. But this allows them to gain those electrons very easily to increase their stability. Now, this trend does make sense because atomic species naturally move to states that have a higher stability. So if the metallic atom is more stable than the metallic ion, the ions are going to react to become that stable metal atom. So they're going to undergo that reduction very easily. Now, is it possible for a metal to be more stable in its ionic form than in its unchanged form? Yes. So, for example, take a look at iron. If the metallic atom, in this case iron, is easily oxidized, can be easily oxidized, that means it could easily undergo corrosion. Now, iron, if you don't protect it, will corrode very easily. And so that's where we would get things like rust, as you can see in this diagram here, where this is rusted iron. Now, iron is a very strong metal. It is a very useful metal, but we have to protect it to make sure that it doesn't rust on us and undergo this oxidative corrosion. So how do we sort all of this out? So two general rules that govern the reactivity of metal atoms and their metallic ions. The more stable the atom is, the more reactive it is as an ion. Whereas the more stable the ion is, the more reactive it is as a metal. Uh, Silver is a very stable atom. So silver ions react very easily. Iron ion, iron 2 ion specifically, is a very stable ion, which means iron, the metal, reacts very easily to make the uh, to make the iron 2 ion. So if we created a list of metal ions from most reactive to least reactive, we also have a list of metal atoms that are least reactive to most reactive, and we've actually done this. Um, to follow up with this, you can take a look at pages 22 to 25, or sorry, pages 77 to 79 and questions 22 to 25. We'll do a little bit of that. But let's take a look at the table that we're talking about. So you have this table in your data booklet. It's going to be on page 4. So maybe take a moment, take that right now. You'll notice I've only given you 3 of the many different ions and metals. Gold ion is right at the top. But by the way, this table is called the table of reduction half reactions. And so you'll see gold 3 ion gaining 3 electrons to become gold metal is right there at the top. Copper 2 ion gaining electrons to become copper metal, it's just a few rows down. Way at the bottom is lithium ion gaining an electron to make lithium metal. Now that means as we go down, we're going from the most reactive metal, or sorry, the most reactive ion, to the most stable ion. So gold 3 wants to reduce. It wants to gain those electrons and become solid gold. Lithium ions, not so much. They are extremely stable. Now, likewise, if you were to take these arrows and reverse them, you would have a table of oxidation half reactions. And then the order is just the opposite. Most reactive metals are going to be at the bottom of the table. Lithium is really hard to find in nature because it reacts very easily. You put lithium in water, it's gonna react and dissolve in that water. All of our alkali metals, everything in that first group, like sodium reacts very quickly. Potassium reacts quite quick. In fact, sodium and potassium metal, when you put them in water, they actually react somewhat violently. Sodium will just kind of spit around. Maybe in class I'll show you a video about that. But potassium metal will like start to like create purple flames and that. Now in our table in our booklet, we only have lithium and sodium as our ions, or our very reactive metals. Calcium is also a very reactive metal as well. Yeah, here we see it. So here we see gold is up here. So this is our most reactive, and then this is our least reactive. And then on the other side, gold is our least reactive metal, and lithium is our most reactive. Now it says increased strength of reactant as an oxidizing agent. Okay, so what does that mean? That means they gain electrons easily. If you're an oxidizing agent, you cause something else to be oxidized. Therefore, you undergo reduction. And on the other side, the metals are seen as reducing agents, meaning they will cause something else to be reduced, i.e., they become oxidized. And so if we can understand this table here, uh, we'll be able to uh, predict what kind of reactions are going to be happening as we look at some of these reactions. So a few little steps and hints, and then in our next lesson video, we'll talk about how we can predict the types of reactions that are happening. But just remember, the reactivity of the metal is going to be shown on the left side of the table, or of the metal ions is shown on the left side of the table, with the most reactive being at the top and the least reactive being at the bottom. And then the metals, it's the opposite. The most reactive is at the bottom. The least reactive is at the top. The less reactive you are, the more stable you are. One list makes the other. Okay, so that's everything on this lesson. In our next lesson video, we'll start applying this, and so if you're given like a solution and between two ionic compounds or two metal and an ionic compound or a bunch of ions and a bunch of different metals, we'll be able to actually figure out who's going to be reducing and who's going to be oxidizing. So that's coming up in our next video. But if you have any questions, feel free to ask. Make sure you get your homework done first, though, because it's hard to know what questions to ask if you haven't done your work first. So we'll see you in our next video.